Welcome to Unique World Education YouTube channel. In this class, we are going to discuss about the chapter of grade 10 physics, magnetic effect of electric current. So the chapter is starting with the concept that we have studied in electricity. The current means the flow of electric charge through a conductor. So here in this chapter, we are going to see the effect of an electric current. So the first thing in the chapter, whenever there is an electric current passing through a straight conductor or a circular conductor, wherever it is, whenever a current is passing through a conductor, the current will generate a magnetic field around it. This is the first topic in this chapter. What is that? Whenever there is a current passing through a conductor, it will generate a magnetic field around it. This is the content of this chapter. To study about that, then the next step is we need to study about the what is the concept of a magnetic field. What do you mean by a magnetic field? All these things we have to familiarize first. So first of all, I have clearly given a picture of a magnet. Okay. So you can see a picture of a magnet, and this is a bar magnet. You know this is a bar magnet. One side is south pole, other side is north pole. So we have a magnetic needle. When I'm placing the magnetic needle just near the poles of the bar magnet, I found that the magnetic needle deflection is more just near the conductor, just near the bar magnet poles. When I place the see here you can see when I place the magnetic needle just near the north pole of the bar magnet, I got this direction. And the first thing in this chapter, again you need to study about what is the properties of a magnetic field lines around a bar magnet. So the magnetic field lines around a bar magnet it is originated from the north pole and it is ending at the south pole. So what is the first point? The magnetic field around a bar magnet is starting from the north pole and is ending at the south pole. And so it's north to south pole. The direction is north to south pole outside the magnet, and direction of this magnetic field is from south to north pole inside the magnet. Inside the magnet, the direction of magnetic field is from south to north pole. The next point about this magnetic field is nothing. It will always form a closed loop. Means when it is started from here, it will not end at any point. Magnetic field lines always form a closed loop. Okay, the magnetic field lines always form a closed loop. Then what is the next point? The magnetic field lines never intersect each other. What is the reason? Because so this is the magnetic field line at this point. I want to find the magnetic field direction at this point. I have to draw a tangent. This is the concept. At this point, I want to find the magnetic field, draw a tangent. So if two magnetic field lines are intersecting at a point, in a single point we will have two directions. That is not possible. So the magnetic field lines never intersect each other. Never intersect each other. So what are the properties? It's a continuous closed curve originated from north to south pole outside the magnet. And inside the magnet, the direction of magnetic field is from south to north pole. Now, okay, so this is all about the magnetic field, and field lines are more strong just near the poles, or else we can see the field are crowded just near the poles. You see the picture? Once again, just listen. The field lines are crowded. You see the crowded means you see the picture here. Here there is a distance between the field lines, but you see near the poles it is crowded. There is no distance between the field lines. It is crowded just near the poles. And this is also, you can add one more point in this one. Now the next topic in this chapter is magnetic field lines due to a current carrying conductor, or else magnetic field due to a current carrying conductor. So the first, I'm just doing a one shot video describing about, so first topic of the chapter is like about the properties of a magnetic field lines around a bar magnet. So bar magnet, it's a permanent magnet, it has a north pole and south pole, and magnetic field lines originated from north and it's ending at the south pole. All these things are describing in the starting of the chapter. Now this is the important topic of the chapter. What is the magnetic field due to a current carrying conductor? So let's take a straight current carrying conductor. You can see this is a current carrying conductor. Here a current is passing from this direction, because this is plus and this is minus. Current is moving in this direction. I am placing a magnetic needle. So here the current flows from north to south pole. So for example, the current is moving from north to south pole. The compass needle moves towards east. Okay, so let's take the first condition. The current is moving from north to east. I found that the compass needle is moving in the east direction. Clear? Now what I did, here I changed the direction of the current. What I did, I changed the direction of the current from south to north pole. So here the current direction is from south to north pole, and I found that the magnetic needle deflection reverses. Initially magnetic needle deflected towards the east. The second case, magnetic needle deflection towards the west. And here I concluded that the direction of a magnetic field around a current carrying conductor depending on direction of current. Clear everyone? So when the direction of current reverses, magnetic field around the conductor also reverses. Clear? So there is an experiment which is given at in your textbook, like the magnetic field around a straight current carrying conductor. All that things are given in your textbook. I will show you that picture here. 1 second. Okay, so here you see the picture. Yes, this is the picture. So this is a usual question asked in the exams. Okay, this is a usual question asked in the exams. What is the direction or what is the shape of a magnetic field around a current carrying conductor? See, when a current carrying conductor is going through when a current is going through a conductor and you place a sheet of paper and you just put some iron filling on the paper, and you can see the iron fillings are arranging in the circular order, or else the magnetic field around a current carrying straight conductor is in the shape of concentric circles. Once again, the current carrying conductor produces a magnetic field around the conductor in the shape of a what we can say, the concentric circles. The second point, the direction of this magnetic field is depending on direction of current. So the magnetic field around around a straight conductor is concentric circles. The magnetic field around a straight conductor is concentric circles. So this is the next question which can be asked. And one more point, direction of magnetic field around a conductor reverses when the current direction reverses. One more point, then if the amount of current is increasing, initially I am putting 1 ampere current, then 2 ampere current. I found that the magnetic field strength also depending on the current. When there is 2 ampere current is flowing through this one, magnetic field strength is more when the 2 ampere is passing through it. So direction also depending on, then amount of current also depending on the magnetic field. So if the more current is passing through a conductor, more magnetic field will be generated across the conductor. So this magnetic field due to a current carrying conductor can be explained using the right hand thumb rule. So what is a magnetic field due to a right hand thumb rule, or how we can state the right hand thumb rule? See, This is the explanation. It is an easiest ways to find the direction of magnetic field associated with a current carrying conductor. Now, how to define? Imagine a current carrying straight conductor is held in right hand such that the thumb points towards the direction of current, then the fingers will wrap around the conductor in the direction of magnetic field lines. So this is called right hand thumb rule, or else Maxwell cork screw rule. See, if you are tied the screw like this, the screw will go into the paper or into the wall. Same as like if you tied your hand like this, the thumb will going up. Means if the current is going up, this is the direction of magnetic field. So if the current is going up, this side I will say into the paper, and this side it is out of the paper. So the magnetic field around the current carrying conductor is going like this. It is in the form of circles. The direction we can explain using right hand thumb rule. So this is the answer. Now let's see what is the magnetic field due to a circular current carrying conductor. Let's see about it. One second. So the magnetic field due to a straight conductor is concentric circle. Now let's see what will be the magnetic field due to a circular conductor. See, I am going to find the magnetic field due to a circular conductor at the center. See, just near, we know that the magnetic field just near the straight conductor will be crowded, but again when you are moving it will be big circles, right? So here also big small circle, but when it comes to the center it become a straight line. So the magnetic field due to a circular current carrying conductor at the center will be a straight line. That's a picture here it is given. You see it is small crowded circle, and you can see it's a big circle. When it comes to the center it become a straight line. So what is the point here? The magnetic field due to a circular conductor at the center will be a straight line. This is how it works. Bend a straight line to form a circular loop and pass a current through it. Hence the concentric circle, every point of circular loop become larger as the distance from the wire increases. It is very clear, right? Take a circular loop. Here it is small circles, but when it comes to the center it become very big circles, and you can see it become a straight line when it comes to the center. Now let's see. So the magnetic field due to a circular current carrying conductor will be a straight line. So once again just listen, the center, the magnetic field due to a circular current carrying conductor will be a straight line. Now if I am using this circular current carrying conductor, one turn, 2 turn, 3 turn, if there is n number of turns in a, and if I am winding like this and if I am passing a current through it, I can call this setup as a solenoid. So now see, due to the first conductor the magnetic field is a straight line, then through all around this conductors the magnetic field will be straight line throughout the whole the conductor, circular conductor. So this setup is called, see, and this is the direction and it looks like, or it resembles to the direction of magnetic field using or because of a bar magnet. So this setup is called a solenoid. So let's see what is a solenoid. A solenoid is a circular or coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. So coil of many circular turns of insulated copper wire. Understood? So circular turns of copper wire wrapped closely in the shape of a cylinder, like this. Closely in the shape of a cylinder. The pattern of the magnetic field lines around a current carrying solenoid similar to the pattern around a bar magnet. Second point we discussed. See, the pattern around a solenoid is look like similar to the pattern around a bar magnet. One end of the solenoid behaves as a north pole. So the one end, because the magnetic field lines is going out, that end we can take it as north pole, other end we can take it as south pole. The field lines inside the solenoid are in the form of a parallel straight line. So it's a common question asked in the field lines in the magnetic field is a parallel straight line and it is uniform. It says that the magnetic field at the center of a solenoid is uniform. Understood. So indicates that the field is uniform at all points inside the solenoid. And if a magnetic material is placed inside a current carrying solenoid, it becomes magnetized. So we know that a uniform magnetic field is present inside the solenoid. Inside the solenoid, if I am placing a magnetic material like a soft iron core or something, that's the second picture. If you place a soft iron core or something inside a solenoid, we will get what we will get? We will get an electromagnet. How? Because when I'm placing a soft iron core inside a solenoid, that soft iron core become a magnet because of the uniform magnetic field at the center of a solenoid. So we have the next topic is force acting on the conductor, that will discuss on the coming videos. Okay, thank you all.